In this snippet, we will be analyzing a Rankine cycle. The analyzed problem is straightforward, but includes a fair amount of detail. The layout of our cycle is shown here, along with some provided data. The inlet to the turbine is saturated vapor at 100 psi. The condenser is at 1 atmosphere. The water leaving the condenser is subcooled with a temperature of 80 degrees Fahrenheit. Also provided are the efficiencies of the turbine and the pump. Shown here is a temperature entropy diagram with labels corresponding to our cycle. Listed are the water and saturated steam properties that will be needed to solve this problem. Listed are the desired results: pump work, heat added by the boiler, heat removed by the condenser, cycle efficiency, and the temperature at the discharge of the pump. The equation for the pump work is shown here. The specific work of the pump is equal to the differential pressure across the pump times the specific volume. This is the energy transferred to the liquid. It is the ideal specific work of the pump. The calculation with units is shown here. Unfortunately, pumps are not 100% efficient. Pump hydraulic efficiency is defined as the ideal work over the real work. If you forget this formula, remember, the larger term always goes into the denominator. We have to put more real energy into the pump to get the desired amount transferred to the fluid. Now let's calculate the energy added by the boiler. A quick inspection of the diagram indicates it is the difference in enthalpies between points 3 and 2. The enthalpy at 2 can be attained by adding to the enthalpy at 1 the real pump specific work which was calculated in the previous step. The calculation is straightforward and shown here. Now let's calculate the energy removed by the condenser. Calculating the energy added by the boiler was rather simple. Let's see if it's the same for the condenser. Once again, inspecting the diagram reveals how to calculate the energy removed by the condenser. It is equal to H4 minus H1. Point 4 is a saturated mixture, so we will have some work to do to obtain the quality at point 4. So we need the quality at 4. What tools do we have in our bag? Well, we know the turbine efficiency. Let's try that. Turbine efficiency is equal to the real turbine specific work over the ideal turbine specific work. Note that this is the reverse or reciprocal of the pump hydraulic efficiency. In terms of efficiencies for this problem, it is equal to H3 minus H4 over H3 minus H4S. We can solve the enthalpy at 4S once we know the quality at point 4S. Point 4S has been added to our TS diagram. The ideal turbine process is isentropic, therefore the entropy at point 3, which is known, is the same as the entropy at point 4S. Now we can use that to determine the quality at point 4S. That calculation is shown here. The quality at point 4S is equal to 0.893. With that, we can calculate the enthalpy at point 4S and substitute that back into the equation for turbine efficiency. Once we do that, we find that the enthalpy at point 4 is 1075 BTUs per pound mass. Now we have enough to calculate the energy removed by the condenser. It is equal to 1026.98 BTUs per pound's mass. Now let's calculate the cycle efficiency. Before we do that, let's go ahead and calculate the Carnot efficiency. We don't know the actual temperature of the cooling water, but we do know that it's less than 80 degrees since the condensate leaves the condenser subcooled to 80 degrees. We'll use that as the best available information. Remember, always use absolute temperature when calculating the Carnot efficiency. The Carnot efficiency comes out to be 31.5%. We have several options to calculate the cycle efficiency, but since we have already calculated the energy in and the energy out, the approach shown here will be convenient. The cycle efficiency is 9.8%. This is pretty low and not surprising since the boiling pressure is only 100 psia. Now let's calculate the temperature at the pump outlet. Big picture, We know that the pump is applying 0.423 BTUs per pound's mass, but only 0.254 BTUs per pound's mass goes into increasing pressure. We will assume that the remaining energy goes into heating up the water. The equations are shown here and provide the details. Let's do one additional calculation. We have everything we need, so let's calculate the real specific work of the turbine. It comes out to be 112.2 BTUs per pound's mass. Recall that the pump work is 0.423 BTUs per pound's mass. It is typical in Rankine cycles that the specific work of the turbine is several magnitudes greater than the specific work of the pump. We often just ignore the pump work with little or no loss in accuracy. I hope you found this instructional snippet useful. If so, please like and subscribe, and have a great day.